Hello, everybody. Welcome to another edition of Bed Talks here. So in our last video, we discussed how to find minimums and maximums on overall, like a local min and a local max, right? How to find critical points. And we saw, just kind of as a reminder, what did we see? Well, we saw that we had this f of x, y, right? And if I wanted to find a critical point to see if there was a low place or a high place, like a valley or a hill or something like that, what we saw is we took the partial derivatives with respect to x, we set that equal to 0. We took the partial derivatives with respect to y, we set this equal to 0, and found all the points such that this admitted an answer. I'll find all the x, y that did that. And then from there, right, we can classify each one. In this case, we would classify each one using the second derivative test that we kind of mentioned, where we take a look at this determinant here. Now, one thing you might ask yourself then, and something that's a little bit more difficult to kind of answer, something we'll tackle in this question, it's a little bit like this. So let's assume that I have this question here, just really basically. If I wanted to find, if I had f of xy is equal to y squared minus x squared, and I told you that I wanted to find a maximum or minimum value of this overall, maximum or minimum value. Well, I hope you'd agree that the maximum value of f of xy here is going to be infinity, because I can just make y as big as possible, and I can let x be 0. So I can let that go off forever. Right? I can make that go off forever, so the highest this could be is infinite. But I could also tell you at the same time, well, I can just make x as big as possible and make this negative infinity. So it really doesn't make sense for me to talk about absolute maxes and minimums, at least in this kind of problem here. And so one thing you might ask yourself here is, okay, well, is there another way I might be able to start to think about how do I maybe contact, or how do I maybe construct maybe absolute maxes or minimums or extreme values? Well, in 2 dimensions and 3 dimensions and so on, we have to usually add a constraint. And so you might see a problem like this, where I have to add this constraint right here, where maybe I could say something, I want to find the maximum and minimum values. I want to find the extreme values of this function on this curve, or with this constraint, where x and y have to be x squared plus y squared equal to 1. It has to be on that circle. And this now can have me, in a really, really interesting way, will allow me to maybe find an extreme value. And see where this comes into play as applications, right? Well, if I have, for instance, if I wanted to find, what's the largest volume of a box that I can construct with a certain amount of surface area, right? If I tell you the surface area of something and I want to find the maximum volume of the box, right, I can kind of do that. It's kind of a constraint in that exact regard. So one way you might be able to ask yourself is, okay, well, I want to maximize this function given all the points that are x squared plus y squared equals 1. And how can I go about doing that? Right? How could I maybe go about trying to solve this? Well, this is the technique of something called Lagrange multipliers, which we'll talk about today, how we do that. And the first thing I want to just discuss here is the technique of Lagrange multipliers, and what do Lagrange multipliers actually mean, just in general. Well, this works for as many dimensions as possible. This works for as many dimensions just in general, but there's usually a certain technique. So let's say my problem is as follows. I want to maximize or minimize, I maximize or minimize a function f of xy with the constraint g of xy is equal to some number k. All right, so I have something like this, where I want to maximize this function, let's say y squared minus x squared, and I want to have a constraint, which is g of xy is equal to k, like that. Which is in this case, g of xy in this problem would be x squared plus y squared is equal to 1. And here's the process that I would kind of use. If I want to try to solve this problem, what's interesting here is we can relate this to the gradient. So what I do to kind of initialize this is I take the gradient of f here. And I basically want to find where the gradient of f and the gradient of g are parallel. Okay, I want to find where these guys are parallel. Now, why is this? Right? Why do I want to find that these are parallel? Well, this kind of relates always to contour lines in the same exact way. So what I do is I basically can plot these contour lines, if I wanted to do that, I can kind of draw this out like this. Let me see if I can kind of draw this out in some way. So I have these contour lines. Like this. And these are the contour lines for f of x. So these are all like f of x, y is equal to k, right? It's equal to some value. Maybe k is not the best letter here. Maybe I should use maybe something like c. I have these contour lines, things like that. And then I have my constraint, which I might draw my constraint as something like this. And what we can find is if I have my constraint here, which this is f, maybe g of x, y is equal to k, my goal then now is to find where these level curves, where the level curves and specifically this constraint are kind of tangent to each other, they're parallel to each other, which means that the gradients at this point, for instance, up here, the gradients here are parallel. You'd agree in this case, because they're kind of tangent to each other, kind of parallel in that case. So we can kind of say that their gradients must be parallel. If the level curves are parallel, they must be, and the gradients must be parallel. So just my ultimate goal is to find where my gradient of f and my gradient of g are parallel. If I can find those points, this actually gives me that all those points that have this process can be maximums or minimums on my constraint here. And there's many reasons why this is. I'm not going to get into technical details. My point of this video is to kind of show you the techniques to solve these problems. But the ultimate goal here is to show and find where these gradients are equivalent or that are parallel. So if they're parallel, as a reminder, how do I know if two vectors are parallel? If two vectors are parallel, if I have A is parallel to B, we know that there's a constant. Usually we call it a constant, maybe let's call it a lambda here, maybe C here, where I can multiply C times my vector B and get it. They're scalar multiples of each other. And so if I want to find here, what I want to find are all the points x and y. This is actually the concept of Lagrange multipliers. The first thing you do is find all points such that the gradient of f is equal to a constant, which we usually denote as lambda, times the gradient of g. Subject to the constraint, g of xy is equal to k. Now, I want you to think about what's happening here. Okay, let's say this is two variables, right? Well, I want to find all points such that this happens. So I want to basically find all x, y, and lambda such that that happens. I want to find all x, y, and lambda that happens here. I wanted to show you why we need this extra constraint. If I write this out, right, I'm going to get fx, fy is equal to lambda gx, gy. Look at something like this. And I hope you'd agree, this, if I wanted these two to be equivalent, I'm going to have a system of two equations up here, where I have to equate the x components, and I have to equate the y components. So I get something like fx equals lambda gx, fy equals lambda gy. But in this case, right, these are all dependent on, I have three variables and I only have two equations. So I need one extra equation. And the way to kind of get this one extra equation is to utilize this constraint. So if you have two variables, you do need three. I mean, if you do have two variables for your f here, you're going to need three equations to solve this out, because I need to possibly solve for lambda. Whenever you're solving Lagrange multipliers, it's never necessary for you to find the lambda. Lambdas are these things called, this is actually called the Lagrange multiplier. It does have a purpose, but for our problems right now, for these problems, it's not necessary to. Sometimes it might be beneficial for you to solve for those lambdas, but it's not necessary. So in this case, we find all these points, x, y, and lambda that do that. If we do that, if we find all those points, we then find their values, find all these points, function values. So we basically plug it in to f of x, y, and then see which ones are maximum. Then see which are max and min. you are guaranteed to use, if you use this technique, you are guaranteed to find the minimums and maxes. Whatever points come up, those are going to be the minimums or maximums here. Okay, so let's kind of tackle some problems here, and let's at least see some processes that you might use to solve some of these problems. I will hopefully give you some techniques on how to do this. What's interesting here, and this is actually utilized in Stewart's, it actually says in Stewart here, if I can read this correctly, there are no general rules for solving the systems of equations, and sometimes ingenuity is required. And it's very true. There's not really always a process to solving this. But I do know the first thing you do is you take the gradient of your f, you take the gradient of your g, you set up your system of equations, and from there, you just have to come up with some process and find all of my points. So let's take this exact example that I kind of already constructed up here, and we'll do a couple more. So, oh, whoopsies, sorry about that. So in this case, what I'm going to do is I'm going to we define this as g of xy. Okay, define this as g of xy. And what I'm going to do is I'm going to take the gradient of both of them. So I'm going to take the gradient of f here, which is equal to negative 2x, 2y. I'm also going to take the gradient of g, which in this case, I'm not taking consideration the 1, right? The 1 is going to come into play later. But in the gradient of g, I'm taking into consideration here, the gradient of g is just 2x and 2y. And now, because of this, I want to find all of the points such that this occurs with some lambda here. In this case, what we do is I can solve this be 2x, 2y is equal to lambda times 2x and 2y. And this then tells me over here, kind of moving over in this direction, if I do this then I'm going to have two equations. I'm going to have two systems of equations. I have negative 2x equals lambda 2y. I'll say 2 lambda x. And negative 2x equals lambda 2x right here. I also have 2y equals lambda 2y. And then lastly, I have this constraint up here. So I need to also solve it like this. And now my goal, I have these three equations. And my goal now is to find all of the points x, y that satisfy this equation. We can also solve for lambda if we need to. Okay, now how do you go about doing this? Well, I think the first thing to note is always, well, I'm going to at least number all of these, kind of make sure we talk about the right equations here, 1, 2, and 3, equations 1, 2, and 3 here. At least in this problem right now, I can take a look at equation 1, and I want to find all the points that kind of satisfy that. Now here we have a problem where I have kind of independent equations for x and for y. As you see here, there's no mixing in x and y in these first two equations. So what I usually like to do, I usually like to take the first equation and try to solve this out. Now be aware that there sometimes are zeros as answers. Zeros can be answers. And it's really important for you to always check if 0 can be an answer before you divide out. Because if you divide out by a 0, right, we lose that solution. It's really important that we don't do that. To kind of counteract that here, what I'm going to do is I'm going to add over, I'm actually going to add over 2x on this equation and kind of factor. So if we see here, I'm going to add this for equation 1. I'm going to get 0 is equal to 2 lambda x plus 2x. And then I'm going to factor out 2x. I'm going to get lambda plus 1 times 2x. And what's important here to note, and this is an example of one time where I probably actually want to solve for my lambda because it's going to be helpful. So because I have two things multiplied by each other, I can solve this out. And I know that this means that this has to be equal to 0 or this has to be equal to 0. There's two solutions here. So this means that lambda plus 1 is equal to 0 or 2x is equal to 0. And this implies that we have a lambda equal to negative 1. And this implies that we have an x equal to 0. So those are two possibilities, just in general. I have that lambda equal to negative 1 can be a solution here. Because what would that do, right? That would give me a negative 2x equals negative 2x. And that's true for all x. right? So that also makes sense. And so here what I'm going to do is I now have two roots. I know that these are the only two options. I can either have lambda being -1, or I could have x being 0. So let's tackle lambda equals -1 first. If I tackle lambda equals -1 first, I am then going to plug this in to my equation 2. Plugging this into equation 2, I will get 2y equals -2y. And I want to find all the points where this happens. And you might say to yourself, well, where does this actually happen? Well, where's 2y equal -2y? Well, if you want to kind of go for this and kind of figure this out, you can move this over and you'll get 4y is equal to 0. And so y has to equal 0. So if I have lambda equal to -1, I can get that y has to be equal to 0. And so now I need to find my x coordinate. And how do I do that? Well, if I can't plug this back into 1, that wouldn't make any sense because I've already used 1. The only other equation that I have is equation 3 here. Equation 3 here is x squared plus y squared equal to 1. It's my constraint. If I give you what y is, I can tell you what x has to be by using this constraint. So from that, when we plug this into equation 3, and we get x squared is equal to 1. Or more formally, this means that x is equal to plus or minus 1. And what this tells me is that I can have two different points with this lambda being -1, right? This gives me 2 points. This gives me the point, and this is a really, really important fact. I have 2 points. I have 1, 0, and -1, 0. Those are the 2 points that I get that could possibly be maximums or minimums. They could possibly be extreme values for this problem. Okay, now this other route over here, this x equal to 0, I pointed to my screen. Why did I do that? That makes no sense. I was like, look at that. You can't do that. Wow, I'm sorry about that. So x equal to 0. Well, okay, I have x equal to 0 from equation 1. Does this tell me anything about equation 2? No, right? It doesn't tell me anything about that. I have x equal to 0. So my goal is now to just find my y. Once I've found one of my variables in this kind of system, you've got to just go to equation 3. Because once I've done that, I can just get the constraint out of that and solve for the y, or solve for the other variable. That's what we kind of did here, right? We found what y equal to 0 is, and then we plugged it into the constraint after that. So at this point, I'm going to plug it into 3. And we would get that y squared is equal to 1. We get that y is equal to plus or minus 1. Which then this again implies that I have two other points. I have points 0, 1, and 0, -1. And so I have 4 possibilities for my extreme values. I have 4 possibilities. At 1, 0, -1, 0, 0, 1, and 0, -1. As you can see in this route over here, I didn't even solve for lambda. It is not necessary. You do not have to find the Lagrange multiplier. You don't have to find this lambda. In this case, it helped us out. Well, you don't have to overall. It's not necessary to solve this. All you have to do is find the coordinates. So now, with this in mind, the next step we do is we're going to plug in all of these points into my function that I want to maximize, which is f. And we're going to find out which ones are maximal and which ones are minimal. And that's my answer. So now what we do is we take all of these points and we plug these in. We plug in f of 0, 1, f of 0, -1, f of 1, 0, and f of -1, 0. Kind of like that. We plug this in. It's gonna be y squared minus x squared. So this is going to be 1 minus 0. This is going to be 1 minus 0. This is going to be 0 minus 1. This is going to be 0 minus 1. Right? And so this becomes, really quickly, this gets 1, 1, -1, and -1. And so we see here that on this circle, x squared plus y squared equals 1, if we want to maximize or minimize this function, f of x, y, we have to have the maximum values. The maximum values are at 1, or where the function value is 1. The max is where f of x, y is equal to 1. And this occurs, I'm going to write this, occurs at 2 points. It occurs at 0, 1, and 0, -1. And we have minimums, which is f of x, y is equal to -1. That's the lowest value it's going to be. And this occurs at 2 points, 1, 0, and -1, 0. And this is my answer to my question. So kind of the process is as follows. You take the gradient of your function. your first function that you have, your extreme value function you want to try to find the extreme values for. You take the gradient of the other function, which is going to be the constraint. You don't have to include the 1, right? You don't have to include the constant on one side. You just have to take the gradient of both. You want to find where these two gradients are parallel. So what you do is you set them equal to each other with some constant in front. You usually use lambda. You can use any variable you want. Usually the customary thing is lambda. You then solve the system of equations. You don't have to solve for lambda. You don't have to solve for the Lagrange multiplier. Sometimes it's helpful. So I do 2 more problems now to kind of explain to you a couple different techniques here to kind of see this. We're going to do one right now that's a little bit more fancy, and one that's a little bit different. So let's tackle this one. We have a 3-variable one. I want to maximize or minimize this function right here. F of x, y, z is equal to xy squared z, subject to the constraint of x squared plus y squared plus z squared is equal to 4. Okay. I would like to maximize or find the extreme values of this function subject to this. Now this is a 3 variables. This becomes a little bit more taxing here, but we could still kind of go ahead and do it. So it's the same exact process as we had before. I'm going to name this function g of x, y, z. What is this again? This is actually a sphere. So we're just trying to find where are these values, where's this function maximal on a sphere of radius 2. Kind of my goal. So what we're going to do is we take the gradient of f here. The gradient of f here is going to be a 3-dimensional vector, which is y squared z. We then will get 2xyz. And lastly here, we get xy squared. The gradient of g is going to be equal to, actually pretty nicely, 2x, 2y, and 2z. And so therefore, because of this, we can get our system of equations then. We will get that I need my gradient, which is y squared z, 2xyz, xy squared equals lambda times 2x, 2y, 2z. So I can set up my 3 system of equations here, my 3 equations for this system. So the x components have to equal each other, which means that y squared z has to equal 2 lambda x. We can get 2xyz has to equal 2 lambda y. We then can get, lastly, xy squared is equal to 2 lambda z. On top of this, I now have 4 variables, right? X, y, z, and lambda. So I need a fourth equation, which is going to be this equation, my constraint. And this is the system of equations that I necessarily need to solve now. I'm going to number these because we're going to need to talk about them individually. And so this is the system we're trying to solve. So we take the gradients, we set them up, we set up this system. Now, with this in mind, this is actually really kind of an important process here. So to solve this system here, you might say to yourself, how do I even start going about this? Well, the first thing you want to do is to see if I'm able to divide by things. Am I able to divide by x? Am I able to divide by y? Am I able to do these things? And the reason why you want to do that is because, at least in this process here, I see that I might want to try to actually get all of these equations equal to lambda. I think that might be very beneficial. So if I get all these equations equal to lambda, right, on both sides, I can then equate all of them and maybe get some processes together like this. So what am I trying to say about that? Here, if I take equation 1, let's assume, could x be equal to 0? Could x be equal to 0? This is an important question. If x is equal to 0, then what happens? This means that y squared z has to be equal to 0. I hope you'd agree. All right, that's what kind of happens there. Well, if y squared z is equal to 0 here, and I want to try to make this happen, well, there's 2 options. Either y is equal to 0 or z is equal to 0. Right? There's not really any other options there. Right? If I kind of let y be equal to 0 or z be equal to 0 here. Now, with this in mind, if I do that then, well, does anything else fail here? Well, if y is equal to 0, this means that z would have to be equal to 2. I hope you'd agree. in this case, or -2. Now, does this make sense in terms of everything? Well, if I actually solve this out, then it actually wouldn't make any sense. And the reason is as follows. Because if I now take a look at this route here, if I take a look at this route, what happens? Well, in equation 3, I could actually find that this means that 0 is equal to 2 lambda z. And we always want to find where lambda is non-zero. Because if lambda is 0, this entire system doesn't really make sense because I need to be parallel. It wouldn't make sense in that case. So we always are trying to find for lambdas that are non-zero. So in this case, if I let y be equal to 0, this whole thing falls apart because this implies that z is equal to 0. And this whole entire equation can't happen then because I would just get 0 plus 0 plus 0 equals 4, which can't happen. So this whole route can't happen because of that. So what am I doing here? What am I attempting to do here? This is not completely necessary to kind of do these problems, but I like to at least try to see if I have zeros in this case. Am I allowed to divide by 0? Well, divided by 0 hurt me here. Again, if I go this route, if I now go this route over here, if I take equation 2, this then implies that 0 is equal to 2 lambda y, which again implies that y is equal to 0. And again, this won't work because I would just get 0, 0, 0, and we get that whole thing, which won't satisfy that. So this means that x can't be 0. And this can again imply that x can't be 0, then y can't be 0, then z can't be 0. So because of all of that, and this is a really important part of this, I'm allowed to divide out by all my variables because my variables cannot be 0 and lambda can't be equal to 0. So why does this help me? I'm now going to solve for lambda for my equations 1, 2, and 3. Okay? In 1 here, I'm going to solve this out. This will become just y squared z over 2x is equal to lambda. 2 here gives me, I can actually solve this out. This actually becomes just xz is equal to lambda. Because I divide out by y, and the y's will cancel. I know y can't be 0 because of this whole process here. And lastly, this one right here, this 3 here, will become that this is equal to xy squared over 2z is equal to lambda. Okay, so what does this mean? Well, this means that I can actually equate, for instance, these two variables, these two equations, because they're equal to lambda. So I'm not solving for lambda here. I'm not solving for explicitly for lambda. I'm trying to actually use lambda here as a kind of a pivot point to kind of go into a different direction here. So for this kind of problem, I can set these two equal to each other then. Y squared z over 2x is equal to xz. We can then actually see that I can cancel out the z's. I can go through that. And we can actually get that y squared is equal to 2x squared. Okay. I'm going to hold on to that thought. I'm going to get this. So this is what these two things give me. Now what I could do is I could do the same exact thing down here. Okay. And this could give me that this is xz is equal to xy squared over 2z. Again, I could actually cancel out the x's. I could multiply across. And this could give me that y squared is equal to 2z squared. Okay. So now, what does this give me here? This gives me that I can tell you my relationship between x and y and x and z. And why am I leaving it like this? Well, here's the great thing. Look at equation 4. What I'm going to do now is I actually can start to solve possibly, by plugging in here. I know I have a y squared in here, which I now know that I might be able to, I can actually solve for x squared here. I can actually solve for z squared here if I wanted to do that. So this gives me y squared over 2 is equal to x squared. This right here actually gives me y squared over 2 is equal to z squared. And so what I'm going to do is I'm going to replace my x squared and my z squared in here. And because of that, I can solve for y squared. And therefore, I can solve for y because of that. So what did I do? Kind of just going backwards. One way you can do this, and this is kind of the technique I saw, is that if I let everything be 0, this kind of falls apart. So I can divide out by x, I can divide out by y, I can divide out by z. Doing this, Gale gives me a process here that at least says, okay, well, y squared equals 2x x squared here. And I can then replace my x squared here with y squared over 2. I could replace my z squared here with y squared over 2 and solve the system out. So kind of doing this here. Boop, boop, boop. Over here, I now, for equation 4, I can replace x squared with y squared over 2. I can replace this with just y squared, and this becomes y squared over 2. And this is equal to 4. Just like that. Now here, in this case, we get that this is actually just 2y squared, because this is 1/2, 1/2, and 1. So it's just 2y squared is equal to 4. So y squared is equal to 2. And therefore, y is equal to plus or minus the square root of 2. And so this is a possibility. Y has to be equal to plus or minus 2. Okay. Now, with this in mind, let's kind of just now start to work backwards here. This is actually where it gets fun, because we're going to have a lot of options here. So I tell you now that y is equal to, let's actually first tackle, y is equal to just the square root of 2. If y is equal to the square root of 2, I can then find out what x is equal to by going here. I can tell you that this means that 2 is equal to 2x squared, or x is equal to plus or minus 1. Okay, that's interesting. As well down here, this tells me that for z, it's going to be the same exact thing, where I'll plug into this equation right here. That just gives me that 2 is equal to 2 with z squared, or 2 is z squared, which gives me z is equal to plus or minus 1. And what's really interesting is that I have 4 options now, just in this aspect, because I have that the square root of 2 gives me a possibility of x being plus or minus 1 and z being plus or minus 1. And there's no relationship between what x and z have to be here. They just have to satisfy that, these 2 equations kind of hold. And because of that, I get 4 options. I get I get a plus and plus, a plus and a minus and a plus, and a minus and a minus. So I can get these 4 options. I have 1 square root of 2, 1. 1 square root of 2, negative 1. Negative 1 square root of 2, 1. Negative 1 square root of 2, negative 1. And these are the 4 here. Yeah. This is fun. This is a crazy one. There's a lot of options. The next one here, we can get the same exact process, because I'm going to square these values, and I'm going to get the same exact thing. So I'm going to get 2 equals 2x squared. 2 equals 2x squared, which gives me x equal to plus or minus 1. I'm again going to get 2 equals 2z squared, which gives me z is equal to plus or minus 1. I like that. And again, I would get 4 more in the same exact vein. I would get 1 negative square root of 2, 1, 1, negative square root of 2, negative 1, negative 1, negative square root of 2, 1, negative 1, square root of 2, negative square root of 2, negative 1. And so now I have 8 options. All of these can possibly be maximums or minimums. And now I have all of these values that could possibly be my Lagrange. These are the outputs from my Lagrange multiplier method. And now what I do is I plug these into this function. I'll write the function down here because we've kind of migrated down here. So we have a function value x, y, z, which is equal to x, y squared times z. And now what I'm going to do is I'm going to plug in all of these values here. And I'm going to name these individually here 1, 2, 3, 4, 5, 6, 7, and 8. So I don't have to write these all again, just so I can kind of at least number them here. We actually see that they're all going to be the same number because they all have the same numbers here. And this is going to be a squared value, just a matter of if it's going to be a negative or a positive. So 1, I hope you'd agree here, this 1 here, this is going to be 2 squared, negative square root of 2, which is going to be 2, 1 times 1, which is going to just be 2 overall. So they're all going to be either 2 or negative 2, because everything is going to just be either negative 1 or 1, negative square root of 2 or 2, or something like that. This second one will give me, because I have a negative here, this is actually going to be a negative 2. 3 here, will admit, because I have a negative here and a positive there, it's going to be a -2. 4 here is going to give me a negative times a negative, which is a positive. So this is going to be a +2 in a similar manner. Maybe numbers weren't the best way to kind of go for this, but so I don't have to write everything again, at least for here. This 5 here, negative square root of 2 is going to get squared out. So the negative will stay there, will go away. And so I'm left with 1 times 2 times 1, which is just going to be equal to 2. This one right here is going to, again, be a negative. So it's going to be a -2. This is, again, the 7 is going to be a -2, which is a -2. And down here, this is actually going to be, I have a negative times a positive here. So it's going to be a positive value, which is a 2. And so what does this all say? This says that this function on my sphere, I tell you on my sphere, I want to maximize this function here. On this sphere, we do get that I have a max value of 2. And it occurs in 4 places. It occurs at the places of 1 square root of 2, 1, of -1 square root of 2, -1. It occurs at 1 negative square root of 2, 1, and 1 -1 negative square root of 2, -1. And we also have a min value of, in this case, -2. And these occur at the other ones, where I get -1 square root of 2, 1, 1 square root of 2, -1, -1 negative square root of 2, 1, and -1, I'm sorry, 1 negative square root of 2, -1. And this is my answer here. Max value of 2 and minimum value of -2. Okay, wow, that was a fun one. It's a really long one, but this is at least the process of Lagrange multipliers as is. And when you're doing these kinds of problems here, this is the exact process you need to take. I actually like this process the most, especially with these really complicated questions. So I've shown you 2 techniques, really. The other one you can do with this, I'll show you one last one to start a little bit quickly. So this video isn't too long. But I just want to show you one last technique here, but at least to show you what we did here. What we saw is if I wanted to divide out by variables, one quick way to do this is to just check if x can be 0, y can be 0, z can be 0. If these things fall apart, which they do here, right, because I don't satisfy this constraint, well, then I can divide out. I can solve for lambdas and then have fun kind of manipulating them, the equations and equating them, just in general. We have 8 equations down here. It's a lot. Late problems down here. It's a lot. We have to kind of check everything. So yeah, so your answers, if I'm trying to find the max and min values, are the actual function values. Don't say your max value is 1 square root of 2, 1. You're actually trying to find the max value, which is 2, and the min value, which is -2. If you're asked where, then you plug in the points. Okay. With that in mind, I'm going to do one last one here, at least for you guys, so you can at least see maybe a more normal kind of question, no, not a normal question, but at least one last technique here that you can maybe utilize. Because there are just a lot of just random techniques that you can use overall. That there's never really a set technique, unfortunately, for these problems. A lot of sometimes ingenuity is just needed. And it is unfortunate, but I think, you know, these problems, though, are just really difficult to solve just in general. I have a friend, I have a researcher friend, actually she's in my office, that does Lagrange multiplier methods. She tries to optimize things. And she does it with 5 variables and 6 variables and uses a lot of constraints, and it gets really crazy. There's many different constraints and all that, and you have to satisfy it. And these problems are really, really real life applicable, as we kind of had mentioned. So lastly here, let's say I wanted to maximize f of x, y as x times y, and I want to have this subject to this constraint of this ellipse. Here, 4x squared plus y squared is equal to 8. So again, we define this as g of x, y. And what I'm going to do is I'm going to calculate my gradient of f, which in this case, the gradient is pretty nice, which is just y comma x. The gradient of g is then equal to 8x comma y, 2y. And then therefore, we can kind of just satisfy this Lagrange multiplier method, which is the gradient of f equals the gradient of g times the Lagrange multiplier. Which one will give me, right? It will give me y is equal to 8 lambda x. And it will also give me then x is equal to 2 lambda y. And lastly, it'll give me this constraint, which is 4x squared plus y squared is equal to 8. Okay. So here, I guess for this problem, how do you start to go about solving this system of equations? So there's a couple different techniques to utilize here. There's never really one that, again, there's never really one problem that you can use. But I like to maybe utilize in this case, I'll show you maybe one technique here that you might not really think about. But at least one that comes up to mind when I kind of do this problem here. The first thing I want you to note is that if x is equal to 0, do you agree this implies that y has to be equal to 0, right? Right. And so therefore, if I kind of do this down here, it doesn't really make sense, right? Because this would mean that 0 and 0 and 8, this can't happen. So x can't be 0 and y can't be 0, just in general. And so what I could do is, if I wanted to, I could divide out by x, I could divide out by y, I could do anything like that if I wanted to. So what I'm going to do here is I'm going to divide out on both sides by, and I'm going to get lambda equal to a number, right? Or with some variables here. I'm going to solve for lambda on both sides. So I'll name this 1, 2, and 3 so I can define these. So equations 1 and 2, I'm going to solve for lambda. I'm going to get lambda is equal to y over 8x. I'm also going to get lambda is equal to x over 2y. And because of this, I can equate both of these. I get y over 8x is equal to x over 2y. That's not too bad. I can cross multiply here. I can get 2y squared is equal to 8x squared. Or maybe more formally, y squared is equal to 4x squared. And now what's really, really nice, I hope you'd agree, is I have this system and I have this last constraint. And what's really nice is I can just replace, for instance, y squared with 4x squared or 4x squared with y squared and go from there. Here, though, what I'm going to do is I'm going to replace y squared with 4x squared. In doing so, I will get that this is 4x squared plus 4x squared is equal to 8, just by replacing y squared with 4x squared. I will get this is x squared is equal to 1, and so x is equal to plus or minus 1. You could do that. And then the other technique you could utilize, if you wanted to, then what we do is I have x equal to plus or minus 1. This then gives me a couple of ideas, right? If x is equal to 1, this gives me that y squared is equal to 4. That gives us y squared is equal to 4, which gives me well, y is equal to plus or minus 2. So I have two options. I have 1, -2, and 1, 2. If x is equal to -1, I again that y squared is equal to 4 again, and I'll get that y is equal to plus or minus 2. So I can get -1, 2, or -1, -2. These are my four possibilities. And again, from here, what I would do is I would plug these into this function and kind of see which is the maximum and minimum. And these are just multiplying the two variables together, right? Multiplying the two coordinates together. So you can kind of see that this will give me a -2, this will give me a 2, this will give me a -2, and this will give me a 2. So these two right here are the ones that will give me maximum. These two here are the ones that will give me minimum at -2 and 2. Now, another way you could solve this, just to show you maybe a different technique, if you're like, I don't know, I didn't really like that technique. I didn't feel comfortable with that. I didn't feel, maybe you want to see a different way of solving these things, just totally okay. You could, again, if you wanted to, maybe go about doing this. So what I could do here is I could actually replace, something you could do, you could replace this 2 here, it's a 2. I'm going to replace x up here. Okay. So I have that x, I have x is equal to 2 lambda y. So I'm going to replace x here in this equation 1. Now get y is equal to 8 lambda 2 lambda y. Okay. So I'll get that. Now, with this in mind, what you could then do is I could divide out by y. I know y can't be 0. So this gives me 1 is equal to 16 lambda squared. So I could solve for lambda. And this could give me lambda squared is equal to 1/16, or lambda is equal to plus or minus 1/4. From here, what we could do is if I do this, what I could do then is I could plug in this lambda equal to 1/4 into really either of these and get a relationship between x and y. That's what I could do. So what am I talking about there? Well, let's take a look at equation 2 then. Well, this would mean that x would be equal to, if I wanted to use, let's say for instance, I'll use lambda equal to 1/4 first. Lambda equal to 1/4 first would give me x is equal to 2 times 1/4 times y. Okay, which would then give me here, if I kind of wrote this out, which would give me x is equal to 1/2 times y. Or maybe I could just write this more succinctly as y is equal to 2x. And if y is equal to 2x here, right? If y is equal to 2x, well, what I could do is I now have this last constraint here, which is right here in equation 3, and plug in y is equal to 2x. And so let's do that. We can then plug this into constraint 3, which could give me that this would be 4x squared plus 2x squared is equal to 8. And we get that 4x squared plus 4x squared is equal to 8. And we're right back in the saddle where we were back then, equals plus or minus 1. We would then plug this back in, we can get our 2 points. And so then we could do the same exact thing with the negative 1/4 and get the same exact idea. We get y equals to negative 2x and then get our points too, right? This would give me 1 would give me negative, would give me 2, negative 1 would give me negative 2. The other would flip that. And we would get all these 4 points again. So you could go ahead and try to solve for your lambdas. These lambdas, these Lagrange multipliers do have meaning. Not necessary to kind of understand what they really mean at this point, but they do give some insight as to maybe, what kind of problems you might have, and kind of, this is a different way to solve it, at least here. If you didn't see this technique that we just kind of did right here, which I think is actually a pretty common technique that I would suggest doing, see if x is equal to 0 and you can divide out. That usually simplifies things. And then, you plug these things in and you go from there. Or you can solve for the Lagrange multiplier specifically, and then work your way down. There's 2 ways. That's basically the Lagrange multiplier method. Yeah, so I think that's really it for this kind of problem here, at least for this kind of technique here. This is a way to solve problems with constraints. You need to set, basically the goal is you have a function you want to have the extreme value of, you have a constraint, you take the gradient of both of them, you want to find where the gradients are parallel to each other. If they are in the same direction, it's usually going to denote a maximum. If they're in the opposite direction, it's usually going to denote a minimum. This is what it's going to entail. And so, yeah, you solve out the system of equations. We have shown you a different kind of techniques to kind of solve that. We had a really long one down here to kind of see with 3 variables. But over here, we had one that was 2 variables and used actually a pretty similar technique to the one in 3 variables. I usually like to tend towards seeing if I could equate the lambdas. If I have lambda equals something, and then kind of equating things as we did here or as we did here. That's my preference. I know many people that do like to solve for lambdas and go from there. Okay, so that's kind of it. I hope you guys are doing well. Enjoy your Sunday, and let me know if you have any questions. Have a good one.